Welcome back. I promised another example on the chain rule, and I'm actually going to use that example to introduce some new topic here that will be of special importance later on when we talk about integration and optimization a little more. So that introduces a new section, 13.6. We're going to talk about polar coordinates today. So, so far we have talked about Cartesian coordinate systems. That means we have two directions that are usually perpendicular to each other, but of course that angle may vary. So we've seen transformed versions of these coordinate systems in the linear algebra part already. We've also seen that in the part on diagonalization of matrices, for example, to decouple differential equation systems. What all of these had in common was basically in the plane we had two directions, and the coordinates of a point were determined by values on these directional axes. What we are going to do now is we're going to introduce a different system. It's called the polar coordinate system. And in this system we are going to determine a point not by giving directions on axes, but instead by giving a distance from the origin and an angle, so a distance from the x1 axis if you want. Let me make a quick sketch of that before I make that more precise. So the general idea here is we have a coordinate system like this. So this is the traditional Cartesian coordinate system. And instead of using that, if we want to specify this point here, what we are going to do is we're going to specify that through the distance of x from the origin. This is going to be called the radius of x. And we're going to specify it through the angle between that line here connecting x to the origin and the x1 axis. And this is going to be called the angle or argument of x. And of course, through specifying these two things, the argument and the radius, you can again specify each point in the plane. The specification might not be unique, because, for example, for this x here, instead of giving you this angle, I could also have used that angle here. Okay, so I can use a positive or a negative angle, it doesn't matter. So uniqueness is lost somehow, unless, of course, you restrict the angle suitably. But you can reach every point, and that's the idea of polar coordinates. And these polar coordinates are sometimes of interest because they make things easier to describe if we're talking about phenomena that actually happen in a more or less circular fashion. For example, if we're describing a movement on a circle, like in a very simplified fashion, the movement of planets around the sun. It's not actually a circle, but you can imagine that, you can generalize that suitably. Or there are many fields in physics that have this radial character. For example, electric fields. Yeah, they get weaker with increasing radius, or gravitational fields get weaker with increasing radius. So it's probably a good idea to describe those in a system that somehow accommodates for that. And polar coordinates are what is suitable here. So that often makes it easier to capture phenomena like this, and that's why you would like to be able to do computations with polar coordinates. Okay, let's make a few notes of what I just told you. So far we have used classical Cartesian coordinate systems. or linear transforms of those. And the polar coordinate system is not a linear transformation anymore. Okay, however, in some situations, let's just say other coordinate systems can be more useful. Can be more suitable. And as a first example, we will consider polar coordinates in the plane. Okay, I just said those are often handy to describe forms and motions that have a circular nature. For example, the motion of planets in a very simplified way. Or electric fields, or also gravitational fields. And many more. We'll see some more examples later on in this course. Okay, so instead of these classical Cartesian coordinates, we describe a point in the polar coordinate system through the following two characteristics. First is the distance of the point X from the origin, and that is called the radius, and we usually denote it by rho of X. And second, the angle between the x1 axis and the vector pointing to X. And that is called the angle or argument. That will be denoted by phi. Okay, more formally, if you want to compute that, what do we have to do? Well, formally, let's say we have a point X that in classical Cartesian coordinates is x1, x2. what is the relation between those Cartesian coordinates and the polar coordinates? The relation between Cartesian coordinates and polar coordinates is, well, let's see how we can get that. Again, let me draw the classical coordinate system first. Then we'll take a point somewhere in that system, this one for example. Then of course what we have is the radius of that point. That's easy to get. Just measure that distance here. So that's the radius rho. And it's just the distance. And then we have the argument phi, this one here. And the question is, how are these related to the Cartesian coordinates? We have here the x2 coordinate and here the x1 coordinate. Well, as you can imagine, that relation has to do with sine and cosine. You do remember that this x1 coordinate here, this is basically the cosine of phi if the radius is 1. If the radius is not 1, then of course we'll have to scale this by the radius. And this x2 coordinate, this here, that is then the sine of phi, again scaled by rho. Okay, so there is the relation between those two. So x1 is rho times the cosine of phi, and x2 is rho times the sine of phi. So these two equations connect Cartesian and polar coordinates. And of course we can use that to solve for one or the other. Now what happens if we have a mapping given in Cartesian coordinates and we want to transform it to polar coordinates and then maybe compute derivatives with respect to the polar coordinates? How can we do that? Well, let's try that. So if f, let's say a mapping from R2 to R is given in polar, not in polar, in Cartesian coordinates, and we would like to express it in polar coordinates. Then of course we can do that by using the respective mapping. By using the mapping H that maps from polar coordinates to Cartesian coordinates, and that is defined just as above. So H of rho and phi is defined as rho cosine of phi, rho sine of phi. Okay, so this transformation is then f after h is f expressed in polar form. Okay, and now let's say we want to compute the gradient of that new polar form of f. So what about the gradient of f after h at a point rho and phi. Well, if you want to do that, then we can easily do that by using the chain rule, right? So this gradient, or the transpose of that gradient rather, that is equal to the gradient of f evaluated at h of rho and phi transposed times, now we need to differentiate the inner function, times the Jacobi matrix of h evaluated at rho and phi. And that Jacobi matrix of h, can compute that easily. Remember, here is h, so that's rho cosine of phi, rho sine of phi. So let's start with the first rho cosine of phi. If we differentiate that by rho, then we get cosine of phi. If we differentiate that by phi, then we get minus rho sine of phi. And for the second row, this one here, rho sine of phi, differentiating by rho gives us sine of phi, and differentiating by phi gives us rho cosine of phi. So that is the Jacobian of h. And of course we can just do this multiplication, the scalar product here, and then get the respective gradient of the f expressed in polar form. Now, instead of doing this in this general way, let's just see a simple example of how that can work. Let's say we are looking at a function f defined on R2. And let's say f of x1, x2 is defined as x1 squared plus x2 squared. Very simple. Okay, and what we like to do is we'd like to find out about the gradient of f expressed in polar form. So let's first compute the gradient of f in Cartesian form, because that's how the function is defined. It's easier to see. So we have 2x1 here and 2x2 here. That's the gradient in Cartesian form. Then, to get the gradient of f of h of rho and phi, what we have to do is apply chain rule. So let's transpose that first, because we want to use it with differentials, and that's the transposed version. So that means we need to differentiate f first. So that's the gradient of f at h of rho and phi transposed times the Jacobi matrix of h at rho and phi. So we know that gradient of f, we've just computed that. So here's the gradient of f. That means we just have to substitute h of rho and phi for x1 and x2. Remember, h is looking like this here. Rho cosine of phi and rho sine of phi. So let's do that substitution here. Then what we get is 2 times rho cosine of phi and 2 times rho sine of phi. That's this gradient transposed. And the Jacobian, we have computed that before. Remember, that was cosine of phi minus rho sine of phi and rho cosine of phi. So we just need to do that multiplication here. And well, what does that yield? That is 2 times rho times cosine phi squared plus 2 times rho times sine phi squared. So that's the first component here. We're getting 1 row, 2 columns, so that's the first column. And the second column is then going to be minus 2 rho squared sine phi cosine phi plus 2 rho squared sine phi cosine phi. So what we can see is in the first column we have 2 times rho, and then sine phi squared plus cosine phi squared. In the second column we have minus 2 rho squared sine cos plus 2 rho squared sine phi cos phi. So that cancels out and we get a 0 here. And finally, this expression here, sine squared plus cosine squared, that's 1. So what we get is 2 rho and 0. Well, that's the gradient of f in polar form. That looks quite easy. So you can see that f seems to be suitable for polar coordinates. And let's have a quick look of why that is the case, just to see why this works so well. That is because f, you remember that f was defined as x1 squared plus x2 squared, which is basically the norm of x squared. So in polar coordinates, what is that norm of x squared? Well, that's just the radius squared, right? So if we take f after h of rho and phi, what we get is rho squared. And then, of course, it's not surprising that the gradient in polar form looks so nice. Yeah, that's just because a function in polar form looks so nice. So that's an example for a function where polar coordinates are very, very suitable to describe it. Okay, so that concludes this first discussion of polar coordinates. We are going to extend that a little to the three-dimensional case. And that will give us 2 new coordinate systems. So we'll talk about cylindrical coordinates and we'll talk about spherical coordinates in one of the next videos. And after that, we are going to apply our knowledge on differentials to optimize functions. What we want to do in the end is we want to find optima, local minima, local maxima. We want to characterize these points and we want to use that for optimizing functions of practical interest. For example, we want to optimize profit, production, and whatever you can think of in multivariate cases. And that will be the main topic of the coming weeks. Okay, I'll see you in one of the next videos. Have a nice public holiday if you're watching this before the public holiday. And otherwise, have a nice time in general.